have here with me Team 152, Ryerson. Does that sound right?
Yep, that is
Yep.
correct.
Excellent, excellent, awesome. All right, and does this look like your whole team, or are we still waiting on anyone?
Nope. This is everyone.
Okay, great. All right, let's get started then. Looks like you were shooting for the 30,000 foot target apogee. Let's see. Remind myself which rocket I'm looking at. What year is this for you guys at the Spaceport America Cup?
This would be our. It's either fourth year, I believe.
Okay.
Yeah, it's either fourth or fifth.
Okay. I think I gathered that you'd been multiple years, but I wasn't quite sure. So you had listed it as, it looks like you have a target apogee of 31,459 feet, right? So we're like 1,500 feet over. And you found that in the past, your estimates were too high, so you're trying to sort of account for that, or you're trying to account for some like mass additions near the tail end of build. Is that right?
Yep, that's correct.
How far into build did you guys get?
So we had the actual airframes manufactured, and we had the bulkheads ready. But after that point, that was when the university actually shut down. So after that point, we haven't really been able to do much manufacturing. So then we just kind of went over the numbers again and worked, on the report and the things that we could do from home.
Yeah. Were you able to get any component testing done?
So usually component testing for us happens later in the year, so around the January time. So that's when we actually have the components manufactured. So with the recovery bay, that's when we determine how much black powder we actually need to separate the two pieces for it. So unfortunately, because we haven't have that opportunity yet.
What about like the parachutes or anything like that? Were you able to do any, or the payload? What is your payload? I'm sorry.
The payload is a deployable glider.
Okay.
So UK, if you want to talk a little bit about the tests we had for that.
Yeah.
Right. So before the pandemic, we were able to make a couple of prototypes, and we were able to test fly them. The test flights demonstrated that the payload was capable of takeoff, gliding, cruise, and flight. Or just the tests were successful. Unfortunately, when it landed, it shattered into a bunch of pieces because it was a prototype. But the prototype looked really, really hopeful. The plan before COVID hit was to reiterate the prototype, make sure it proceeds as planned, make sure what went wrong, and then hopefully build a final model. Unfortunately, campus closed, so we didn't have the option to.
What was the glider made out of?
The glider was made out of, so the spars are carbon fiber with a foam, I guess, panel, and then encased in fiberglass.
Okay.
Yeah, so lightweight, durable, and it should be able to withstand the ejection from the recovery.
And what altitude would that deploy at?
That will be deployed at 1,500 feet when the main chute deploys as well.
Okay.
Yeah.
Great. Okay. And then tell me a little bit about your parachute, the parachute you selected.
Yeah, so Ham, if you want to talk a little bit about the parachute selection.
Yeah, so we have two parachutes. We have the Jogue and the main. The Jogue is a 24-inch, and then the main is 120-inch. And then they're the same parachutes that we've been using year over year at Spaceport. Okay. They're made from like ripstop nylon, and then they're stitched with Kevlar thread, and their shot lines are made from tubular Kevlar.
Okay, great. Oh, I did have a question more about that target apogee. So you had decided that if you found that you did not make it, that you came under mass, you were going to be your target was going to be too high, you were going to add weight to the nose cone. Did you do any sort of calculation simulations about how much weight you would need and how that would affect your center of gravity?
Yeah. So the mass would need to increase. So assuming the weight we had right now, there was no mass creep, we would have to increase it by about 2 to 3 pounds. And so the way the nose cone is actually manufactured, because we're following a process from previous years, we can actually trim it down, and then the actual tip of the nose cone, which is steel, and we manufacture that from a lathe. So because that's kind of like the last bit, if the rest of the rocket after we build it is let's say there's no mass creep, then we can manufacture the steel tip of the nose cone to the proper mass that we need it to be, and then install it. In terms of how it affects the CG, it actually increases the stability a little more, just because you have that heavier mass at the front.
And we can quickly kind of see that with like softwares like OpenRocket, where you can just kind of like manually add in a block of mass at the tip, and you can kind of automatically visualize how the CG moves and how it affects your stability.
You didn't see any need to add any mass to the aft section to accommodate that?
No.
Okay.
We're good for stability for the stage.
Okay, great. What about the fins? What is the fin material and how do they connect to the body?
So the fin material is made out of carbon fiber as well. There's like a special layout we do. So it has at the bottom like a 1/2-inch fin tab, and there are fin slots in the actual airframe. And then we use like an air epoxy mixture that we usually make like in the lab. And that's how we kind of make the fillets, or the fillets. And then I'm sorry. Yeah, that's how we make the fillets for the fins. We have thought of like having like an extra layer of carbon fiber on the fillets, but we have done like flutter analysis in previous years, and we found that like the flutter occurs at a much higher speed than our flight envelope, and they are pretty well like flight tested. Like we've been using the same manufacturing process and attachment process for the past 3-4 rockets.
Okay. So I guess that brings me to another question I had. What is it about this year's rocket that is a new iteration to previous designs? How has this year's rocket improved on previous designs?
Yeah, so one of the bigger improvements we've had is the actual length. We've been able to get things a little more compact. So specifically with where the booster installs the motor and the, I guess you could say, the bulkhead, there used to be kind of a gap in between there. We weren't really quite sure why from the previous team captain. So we've been able to kind of find these small little nuances where there's like a little bit of space that we can kind of take off to shorten it. So 2 years ago now, I believe it was around like 120 something inches. Now we've reduced it down to like 116. So that helps with the total drag performance. Because in previous years, we've kind of undershot the 30,000 foot apogee, and that was just because of the total length and the mass creep. So that was one of the biggest things we really want to focus on, was to give ourselves that overshoot, like you said before, and then when we actually construct it, then we can get it down to the 30,000.
Yeah, we also tried to push down our length as much as we can through like doing multiple CFD simulations on like different lengths. So that was kind of like a semi-optimization method for our length. And it was kind of like a trade-off between drag and the necessity for that much room.
Okay, so you saw a need for a shorter length in order to improve, so you sort of were able to iterate through that.
Mm-hmm.
Okay, anything else that you can?
Yeah, so we also went over some different like manufacturing methods. So previously we would be using really large, heavy molds. So this is more so on like the manufacturing process, and the effects might not be as visual in terms of the final product. But we've moved over into having 3 printed molds, so something that's a lot lighter, a lot easier to work with. So especially with the nose cone, because it has, you know, an ogive geometry. It's kind of difficult to manufacture with the layups. So switching over to something a lot lighter lets us hopefully have a much better handle on the final product.
We also looked at like a new flight simulation method as well. One of the students, Alex, actually, he worked on a new flight simulation algorithm for our rocket.
Okay. Also, our avionics is balanced better than previous years. We basically decided to collect as much data as possible from the rocket. So that includes like the antenna strength and some thermals, and also improved more on the transmission speed and just effectiveness overall.
You said the nose cone was steel?
The tip is steel.
Yeah.
Mm-hmm.
How is that affixed?
That's fixed through epoxy. Aeropoxy. So you have it's a triangle. Think of like a Christmas tree. So there's a little plug at the bottom, which is then what we epoxy around, and then that inserts into the actual nose cone.
So it's not solid steel. It's a hollow.
The top is solid steel, and then you have like a cylinder at the bottom. Okay.
So it's only epoxied in so it's inserted into the carbon fiber nose cone.
Right? It's Kevlar. No, it's fiberglass and Kevlar, but yeah.
Oh, okay. Thank you. No, I thank you. So your nose cone is Kevlar.
Yeah.
And then, so the steel is a solid sort of cone, and then it's got a cylinder that comes in, slots in,
mm-hmm.
and you just epoxy it in. Okay.
It's epoxy around. Yeah.
Is that a design that was used in the past and worked well, or how was that?
Yeah. It's never come off, and even after it's landed, we found that it was, you know, very much still stuck in there.
Okay. Cool. All right, we've only got a few minutes left. Is there anything that I haven't touched on that you would like to share about your design?
I'm not too sure. UK, do you want to talk a little bit about the payload deployment? Because I think that's pretty cool to talk about.
Right. So the payload ejection sequence covers into two steps. You have the structural bay, the ejection bay, and the actual payload structure itself. The payload, the structural is designed to accommodate all the loads being transferred on it during injection. The injection bay is transferred through, as the main chute is pulled from the rocket, it pulls the ejection, the structural bay out. And as the cord is tensed, the cord actually pushes out the ejection bay, which then pushes out the payload bay. It's a bit hard to explain it in words. I hope that the video we sent kind of covered it. Usually I would have a diagram in front of me and I would kind of show you all the ropes and all the sketches. But yeah, honestly, the concept is pretty simple. It's just that we rely on the main chute to actually pull out the payload, which then turns into a glider.
Okay. All right. No, I think that makes sense. Yeah.
Okay, great. Thanks.
Last thing. In the presentation, I forgot to mention that we have a redundant GPS system just in case ours fails. We'll be using the featherweight GPS, and it's APRS, and we don't need a ham license for it. So, yeah, just there.
Great. All right. This is all great. Well, I think that's all I have, and we are pretty much out of time. I thank you so much for all the hard work that you've done this year. I know it's been a challenging year, and just know that everyone's in the same boat, right? So we are unfortunately not able to get as much launching and building done this year, but I think it was a good year for design. Do you have a lot of team members that are going to be able to be around next year to launch and help pass on all this knowledge?
Yes, we do. We are very fortunate that most of us are still staying around. The people that graduated end up doing masters, so we'll all be around for another year.
Excellent. Excellent. Yeah, we're really hoping that this 2-year gap isn't going to you know, take everyone back too far.
Right. Yeah. Hopefully not.
Yeah. Excellent. Well, good. Well, we look forward to getting to see you guys next year in person. But in the meantime, thank you so much for all your hard work, and go and check out some of the other breakout sessions and enjoy what conference we do have.
Yep. Perfect. Thank you. Thank you for your time.
Thank you.
Thank you.
Yes,
Thank you. Have a good day.
Okay.
Bye.
Bye.
Bye.